lecture. Let me pause just a second and talk about it. All right, we have been discussing velocity and acceleration, and we've talked a little bit about constant acceleration. Now, if you recall, of course, just a quick review, remember what velocity is. It's the rate of change in displacement. Of course, it's the derivative, first order derivative from displacement. I hope y'all printed off your kinematics equations. I wanted to kind of go over them too. I may do that, not today, I'll do it Thursday, okay? I also posted them there in Blackboard too. Then of course acceleration is the rate of changing velocity, and remember it has to be changing, okay, for there to be acceleration. If velocity is not changing every time interval, then you have constant velocity and therefore you have no acceleration, okay? Doesn't mean we're not moving, it just means that we're not accelerating, okay? It's like cruise control on a car, no acceleration, all right? If you're on a flat, straight highway, no acceleration with a cruise set, okay? All right, okay? So constant acceleration then, if we plot, and again y'all, I like graphs. So yes, from your ILD we did, interactive lecture demonstration, and I hope that helped you to get a better understanding of velocity and acceleration. I hope it helped. It seems like it did. Y'all, a few of you were asking some good questions, so so I could stick a graph like this on here and ask you, say, what does this mean? What is this telling you, okay? Notice acceleration versus time, you get a flat line or a horizontal line, okay? Meaning that acceleration is constant. So if we plot velocity versus time, what is that going to look like? I think that's what our next slide is. Yeah. Well, actually, displacement versus time, okay? So here we plot displacement versus time. Now notice that displacement versus time is a what? When we have constant acceleration, there's your quadratic, isn't it? Your parabola, okay? But now remember, that's displacement versus time. And of course, velocity versus time would look like what? Straight line, correct? Because what does a straight line tell us? It tells us that we have a constant, don't we? That there's a constant relationship going on with the slope of that line. No matter what points I choose along that straight line, you're going to get the same answer. Meaning that if it's velocity versus time and it's a straight line, not a flat line, straight line, okay? Then that means that the velocity for every time interval is increasing at a what? A constant rate, right? Does that make sense? Okay, very good. All right. Notice I said increasing at a constant rate. Okay, I didn't say velocity was constant. We gotta watch what we say. We gotta watch our words. Okay. All right, increasing at a constant rate. Now, and of course, displacement versus time is a parabola. Had we done the area analysis lab that I did with the other class, you would have actually plotted this line and then distance. Now notice that's time. Notice that's time. If I square time, then that line becomes a straight line. If I square it, and you may have done that in high school. You may have done that in AP Physics, where you actually plotted the relationship of looking at free fall and doing it displacement versus time as opposed to velocity versus time. And you may have done them both, okay? Okay, and time squared, all right? Now here are our kinematic equations that I do want you to be familiar with, all right? And by the way, please make sure on your formula card that you write constant acceleration. Constant accelerations. Now, and they tell you what equations these are in the text. They tell you what equation, that's the equation number in the text, equation number 2.8 and so on, and 2.12. All right. Now, notice, let's come in here and now watch what happens. What if I take the first order derivative of velocity with respect to time right here? What happens? All right, I take the first order derivative of velocity with respect to time. this does what? Gone, isn't it? Because it's constant, right? See, there's no t, so that's gone. And acceleration, then it becomes what? Acceleration is equal to what? Acceleration, right? Meaning what? There's no time. In other words, it's what? There's no t in my equation after I take the first derivative. So that means acceleration is what? Constant. See, folks, don't forget. Yeah, I want you to remember. If you take a derivative and the variable you were taking the derivative with respect to is no longer in the equation after the derivative, then that means whatever you were taking it with respect to is constant. Does that make sense? That means it's not changing. In other words, time is not a factor here. You with me? Take it. Take the first order derivative, and what do you get? With respect to t, take dv over dt, and what do you get? Well, that's gone, and it's just left with a. All right, now do the same thing right here. Let's take what derivative? If we take the first order derivative with respect to, if we take the first order derivative of displacement with respect to time, then what do we get? We get what? We get V naught, which is V initial, same thing. V naught, V initial, same thing. I can put VI there, same thing. Plus what? Well, then it becomes what? It becomes that equation, doesn't it? Huh? Take the derivative. Take the derivative with respect to time. This term is gone because it's a constant, no t. This is, the derivative of t is what? 1, right? So it becomes V naught. And then look, 2 times a half is what? 1 AT. It becomes that equation. Right? Now take one more derivative again, and what do you get? Well, you got what I just showed you. You get acceleration is equal to a, which means it's constant. Okay? So think about that in those derivatives. When you're taking these kinematic equations and you're doing these derivatives, guess what? That's what you get. Now this one here is just an average problem. In other words, if I wanted to find delta x, I could also write it delta x. Now folks, you need to remember, now all of you had chemistry? Chemistry? Maybe been a while? High school chemistry? Okay. Don't forget that you could write this right here as delta x. Because what does delta mean? Delta means change in, and that is what? X final minus x initial, or x minus x naught. Please understand that the naught, the 0, is x initial, and x is x final. Yeah, I wish we would get some consistency across the spectrum with physics and chemistry books and say, all right, guys, let's decide either we're going to use naught or we're going to use final and initial. Personally, I like final and initial because it is final. You can see the F, final, and I, initial. I like that better. If I wrote a book, that's the way I'd do it. But, you know, everybody's different. All right. Okay. So, this here is, look, this is average velocity. You add them up and divide by 2. That's all that is. Okay? So I can find the change in displacement if I take the average velocity times the time. Well, yeah, duh. Well, where do we get that? Well, look, y'all. Remember, velocity average is equal to delta x over what? Delta t, and delta x is x final minus x initial. Okay? So they just rearranged the equation a little bit, all right? That's all they did. See, look, they took this, solved for x final minus x initial, okay? They took x final minus x initial and solved it right here. What? Velocity average, you can write it this way, times the time. Okay? You can write it that way. You can write it that way. Or you can say, look, velocity initial plus velocity final, okay, times 1/2, which is the same thing as dividing by 2. You know that, okay? So just you know, a little different way you can write these equations, okay? So do not forget that. Now this one right here I kind of skipped over. This one is where we take our, if you pull up the kinematics equations, we substitute in for time, okay? In other words, we solve for, let's see, where is it we substitute in for time? Is it on this equation right here? I believe it is, or this equation. Yeah, I believe it's this equation, and we take this equation and solve it for t and then substitute it. In other words, what are we doing? We're canceling out our time variable. In other words, what? Notice what? We may look at that here in a minute. Notice that there's no time in that equation. Well, Miss Shields, do I always have to have time to find the velocity or the acceleration when we have constant acceleration? No, you don't. You don't always have to. You don't always have to, but sometimes you do. And sometimes you might have to do the quadratic equation to find time, because all you may have is the acceleration and the initial velocity. Do what now? Yeah, okay, good. Where you take the quadratic and then solve for time? Yeah, very good. Yeah, because sometimes you may only be given, you know, acceleration, but you don't know the time, and you need to find, and you're given an initial velocity, but you need to find the displacement, and you have to use time. Okay, well, do the quadratic, and of course you know the negative answer you don't use, because there's no such thing as negative time. You always use the positive answer, all right? I don't know if, I think I have you maybe to do a couple of those later on, okay? Okay, so this equation right here is very useful. We use this one a pretty good bit, and again, you say, well, which one are we going to use the most? Well, you'll use them all, but you're going to probably use this one a good bit. This one's very handy, and you're also going to use this one some too, and that one some, okay? Probably going to use this one the least, but it will be used some, okay? Because again, where does this come from? Well, it just comes from our average equation. Velocity average is equal to delta t over delta x. That's where this comes from, okay? And you say, well, why would we use that? Well, let me give you an example. If you knew the displacement and you knew the time and you needed to find the final velocity, okay? Okay? You see what I'm saying? Well, I know my displacement. I know my so let's say that's 0, and this is 10 meters. And I know my initial velocity was 3 meters per second. And I know my time interval was 5 seconds. What would be my final velocity? Okay? All right? Okay. So again, you know, they wouldn't be there if they didn't all have use, of course. But what makes it very nice is that right there. Now, not constant velocity, constant acceleration, okay? And of course, the units for, of course, that one is what? Meters per second. The units for that one would be what? Meters. The units for this one, after you take the square root of it, would be what? Meters per second. And then, of course, this one, the units would be meters, okay? All right? Okay, so don't forget your units. Okay, let's go ahead and jump into free fall. Now, what do we mean by free fall? An object in free fall is, of course, anything that is under the influence of gravity, and only gravity, okay? Very important. So again, we can demonstrate free fall by releasing an object. Where's my stone at? There it is. you take an object and you let it fall towards the surface, towards the center of the earth. And by the way, all objects fall towards the center of the earth, okay? It is in a state of free fall. Well, what about air resistance? Well, it's negligible, okay? Now, that's not to say that air resistance is not a significant factor when you look at aerodynamics, because of course you know it is. Why do you think they make the cars the way they do? They make planes the way they do. They want them aerodynamic. So yes, at higher speeds, it does become a factor, okay? But right here within a few meters of the surface, it's not that big a deal, okay? The greater the distance and the higher the speed, yeah, it starts to become a big deal. Space shuttle, you can tell I'm old school. We don't even use that thing anymore. It's been retired. When it re-enters the atmosphere at 18,000 miles per hour, you betcha air resistance definitely comes into play, because the shuttle heats up. It basically glows red. The bottom of it does. So yeah, at high speeds, you reach, of course, what's called terminal velocity if you're falling within our atmosphere. And again, that all depends on, and we'll look at this later on, that depends on the shape of the object, what else? The shape of the object, of course, the wind speed. If you have cross winds and that sort of thing, it gets real complicated. But negating that, free fall is gravity only. It affects gravity only. So notice that the change in velocity is what? The same at each time interval. So therefore, that's why we can rightfully say, and we may later on do this, might be one of the ones we do in class, I don't know. You're actually going to be doing it, probably not though. You'll be doing that with your late night labs, so you should be able to get a good understanding of free fall. But what does that mean? That means that acceleration is going to be pretty much constant, okay? Now, needless to say, don't take this, don't take for granted of this. As you increase in elevation from sea level, then guess what acceleration of gravity does? It decreases. It really does. Matter of fact, here on Sand Mountain, where we're at now, it's probably around 9.76, 9.75, somewhere in there, it might be 9.77, somewhere right in there. At sea level, at zero sea level, it's right at 9.8, 9.81, okay. When I was at Jacksonville, we did the free fall lab. We actually measured it, calculated it for second floor Martin Hall. And we measured it, and then we used Helmert's equation to actually theoretically calculate what it is. And you can go look that equation up. It's a big, long equation. But I think we calculated it to be like 9.78, and that was 350 feet sea level. So if it's 9.78 at 350 feet, it's here at 1,070, it's probably going to be, 9.75, somewhere around there, 7.6, somewhere around there, okay. So it does change with altitude, needless to say. Denver, Colorado, it's going to be less, okay. Why would that be important? Well, if you had an old pendulum clock, and that's how you determined your time, and that's all you had, well, guess what? You would have to adjust the length of that pendulum with your altitude. Now, living here, would I really need to change it that much from here to Gulf Shores? No, not really. But, if I go up to Denver, Colorado, a mile high, yeah, I'm probably going to see a little bit of significant change in my time over, I wind it up and let that thing start, and then come back a week later, and it's going to be some minutes off in a shorter period of time. That's why if you ever look at an old pendulum clock, I need one in here in the room. If I knew somebody wouldn't steal it, I'm not talking about y'all necessarily, but I'm just an antique pendulum clock. You have a little fine threaded bolt on the bottom of that pendulum, and you can raise that pendulum bob up or down based on whether it's running fast or too slow. And that's why they built them that way. Every one of them's built that way. So if you're ever around an old one, look at it. An antique one, look at it, okay? Of course, most of them now are electronic, and that pendulum just swings just to make you happy. So, there are still some, they still make some, pendulum clocks that actually are mechanical pendulums, okay? All right. Okay. So, again, we base that on increasing constant velocity, a constant increase of velocity for each time interval. Yes, we see here the demonstration that Galileo did, and yes, he actually did this. And of course, before Newton developed the laws of motion, remember what I said about Newton? Newton said, I stood on the shoulders of giants. Who was he talking about? He was talking about Galileo, and Tycho Brahe, and the other physicists and astronomers that came before him. Okay, he built a lot off of Galileo's work, and so and he gave credit to where credit was due. Now, and please remember that value, of course. And if you've had physics before, you should know this right here. Be sure it's on your note card, okay, on your formula card. Now, notice they didn't put the negative in there. Well, Ms. Shields, why is it not negative? Well, technically it really is, because why? Well, how do you know it's negative? Okay, if I take this rock, and I've already done this, and I let it go, is it going to float? Now, I'm hoping from our little ILD last week that you saw when we did the basketball. Remember we talked about where is it 0? But why is it still showing acceleration? Remember the velocity was 0. It's 0 when it's at maximum height. But why did it continue on with velocity increasing, but in the other direction? Well, because we are under acceleration, and it's constant. And yes, it is downward. It is negative, okay? All right. Well, does it matter? Well, it all depends. Again, as long as you keep your inertial reference frame the same, you can actually do these calculations without g being negative. However, if you do the quadratic equation on that particular problem, you have to keep g negative. Okay. All right. You have to keep the, well, let me do it this way. What is it? What term is it we always want to keep positive when we do the quadratic? The a term, right? And we may look at that later on. Y'all did that, you said, in calculus today. We always try to keep that a term negative, okay, when we work the quadratic, right? Okay. All right. Okay. So that's just one thing to consider, but you can actually do some of these equations, problems. Again, it's depending on what we are solving for, okay? For example, if I just want to know how high an object's going to go, if I toss it up, how high will it go? Okay? All right? And let's say I throw it up and start with an initial velocity of 0, and I throw it up and it goes up for 3 seconds. How high will it go? Okay? Then I can just make g positive there. Okay? I don't have to worry about it being negative. Because again, remember, going up is positive, going down is negative. All right? Okay. All right, but do remember that. Okay? All right, position as a function of time. Now listen, we did this in class. Now notice we plot displacement or distance versus time. And so notice what happens to the curve on our graph. All right? So notice right here, we're moving upward, but notice right here, we're moving downward. And what are we doing right there? We were momentarily doing what? Stopped. Just very momentary, just for a brief moment, okay? Now, what do you notice about both sides of this line right there? They're symmetrical, aren't they? There's symmetry. So what does that tell us about free fall motion? Couple of things. There's symmetry. What else could we say about it? What kind of line is that? Is it parabolic? Okay. Now remember, that's distance versus displacement versus time, not time squared. Okay, time. So we see parabolic motion, don't we? An object in free fall, just like projectile motion. Well, guess what a projectile is under once it leaves a gun barrel? It's under the influence of what only? Gravity. Now, yes, air resistance does come into play. Okay, I mean, if you're shooting an artillery shell 20 miles, you got to wind speed and direction. That definitely has to come. But we're negligible right now. Okay, negligible. All right. Okay. So notice that it is symmetrical. There is symmetry. You say, how do you know? Well, this side is just a mirror image of that side, but flipped over. Okay. Look, the value at this point is the same as the value right across at that point, except one thing would be different. What would the velocity over here be going that way? Negative. That's right. Here it would be what? Positive. Okay? That's the only difference. Okay? Okay. Any questions? All right. So notice now if we do what? Velocity is a function of time. Now notice what happens. Now y'all, this should look familiar. If you go back and look at your handout I just gave you back from the ILD, now I know some of you are saying, well, wait a minute, Mr. Shields, ours went up. Ours went this way. Okay, you know why? Because I had the motion detector on the tabletop, not on the ceiling. If I'd have mounted it to the ceiling, it'd look like that. Our velocity versus time would have looked like that. Okay? And again, where is it 0? Excuse me. What point on this graph, this would be a good test question if I put it on there. What point on this graph could you tell me would be maximum height? Where what? Where would you tell me on this graph we would have maximum height? Up here, here, or right there? Right there. Very good. On the 1.5 second. Very good. Yeah. You understand why? Because 0 velocity. Okay? And maybe I should have mounted it to the ceiling, but y'all, that's a lot of trouble. I don't feel like climbing, get up there. I don't want to fall. So, I mean, we get the same result. It's just flipped over. Okay? All right. All right. And, of course, this is showing you how we can integrate. And I'll tell you what let's do before we finish that, before we go any further with the integration. That's the end of the show. I'm going to pull that up. I don't know if you brought it or not, but let's pull that up in Blackboard. And I'm just going to keep recording, and that way we can have it on video too. And we're just going to go over these equations really quick. Let me see if I can pull that up really fast. Tell you what, let me pause. I want to eat up time here. Okay, as you can see, and again, I didn't want to take time to sit and write all this during class period because it takes up too much time. But it is important that you understand how in the world do we come to these equations. All right, well, and honestly, I like integrating them more than I like deriving them algebraically with derivatives, taking the derivative of it. I'd rather integrate. So notice that we take constant acceleration, and what is constant acceleration? It is the change in velocity versus the change in time. So if we integrate this with respect to time, okay, then guess what? We wind up with what? We wind up, if we integrate both sides, of course, we wind up with what? Well, we wind up with the integral of acceleration with respect to time, integrating it, and the same side doing it with respect to velocity. Okay, all right. Notice what happens to our equation. It becomes what? Well, if you integrate this with respect to time, it becomes what? It becomes velocity. And so we have what? dv is equal to at, and then of course you do the integration, and it looks like what? At minus a0 is equal to vf minus vi, and so we wind up with that equation, vf is equal to vi plus at. All right, now, what happens if we take this equation, and by the way, that's velocity final, not velocity t, velocity final. Then if we take that equation and integrate it, look what happens. Well, what is velocity? Well, how did we get to velocity? Well, it's the derivative of displacement with respect to times. In other words, we're almost doing what? Taking the antiderivative, really? We're going backwards, aren't we? Okay? So look, this becomes dx with respect to what? Changing displacement is equal to what? All of this right here with respect to time, vi plus at. Well, notice what happens to our equation once we do all the integration and substitute in for our final and initial values. We get what? X final minus x initial is equal to vit plus 1/2 at squared minus 0. And of course the 0 drops off. And we have our third kinematic equation, right? Third. Okay? All right, now this next integration is kind of unique in that we do what? Notice we say dv dx with dx dt. Now you say, how did you get that? Okay, y'all. What is this right here? The derivative velocity with respect to displacement. Now notice that. And the derivative displacement with respect to time. Okay, well, it's a unique integration. In other words, reality, what is acceleration? I know it's rate of changing velocity, but what is it though? It actually originates from what? Changing displacement, doesn't it? Because look, if displacement is changing, velocity is changing, and if displacement is still continuing to change, it's not constant, then guess what? Because look, if velocity is increasing at a constant rate, then guess what your displacement's going to be doing? It's going to be changing too. So this is kind of an odd integration, but you go ahead and do it and notice what we're left with. Okay, well we know that what? dv dx is what? If you solve it, if you cross this out, all right, look, we get dv dt, which is what? Acceleration, which is equal to what? V, the derivative velocity, with respect to displacement, okay? Then we integrate both sides, and notice what we come to. Okay, again, integration. And I try to do it step by step, and I hope my steps are clear. We integrate. Okay, see right here? We take this right here, take that right there, integrate both sides, and look at what we come to. A final minus A initial is equal to 1/2 VF squared minus 1/2 VI squared. Okay, well, initial acceleration is 0. Okay, but notice it's AX and AXI. Well, look, if you factor that out, if you factor out X final minus X initial, that's delta X, y'all. Do you see that? X final minus X initial is delta X. And then solve for final velocity, boom, there you have that equation. So that's one way of doing it. Now, y'all, hint, 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 I just might on your exam, this first one, give you a bonus, and I may start right here and say, okay, or excuse me, I may say, given this, show me how this equation is derived. I might put V final minus V initial plus AT and say, okay, show me using integration or algebra how we get this equation. All right, algebraically, all right, look, if we do it algebraically, notice we take what? We take a trapezoid, don't we? Now, does it matter which one we do first? No. We just need to remember that this right here, velocity average, is equal to the change in displacement over time. Okay? Well, using the trapezoid method, notice we come to this equation right here, which is our what? Our average, the final displacement using average velocity. Okay? All right. If we move on and take this equation and solve for t right here and substitute it, then notice what we come to. We come to our V final squared and V initial squared equation. And then if we just take our acceleration is equal to change of velocity divided by time and extend it, and we take this area and this area, we come to that final equation, x final is equal to x initial plus VIT plus 1/2 AT squared, okay? And again, showing you how do we get change in velocity? Well, from initial to final, change in velocity. And the area right here is equal to what? Well, if you take the velocity times the time, you come up with delta x, okay? So basically what this equation here is the addition of this rectangular area and the area of this right triangle. Okay? Because what is the area of a right triangle? 1/2 the base times the height. Okay? Okay, I hope that makes sense. So just a couple of different ways you can derive those, and it can hopefully give you an understanding of how we get those equations.